Okay, we will go through some important point in class 12 physics chapter 5 magnetism and matter. Okay, in this figure the arm of the statue of the mounted in the chariot always points to the south. See, earth behaves as a magnet with a magnetic field pointing approximately from the geographical south to geographical north. So Earth's magnetic field pointing from geographical south to north. So we cannot isolate the magnetic poles. We cannot isolate the north or south pole of the magnet. If a bar magnet is broken into two walls, we get two similar bar magnets with somewhat weaker properties. Okay, unlike electric charges, isolated magnetic north and south poles known as magnetic monopoles do not exist. Okay, magnetic monopoles do not exist, but there exists a electric charge. Positive negative charges exist, but in magnetic monopoles do not exist. Okay, this is the bar magnet. It behaves like a dipoles. See the ion fillings. Arrangement of the ion fillings is surrounding a bar magnet. This pattern mimics the magnetic field lines. The pattern suggests that the bar magnet is a magnetic dipole. Magnetic field lines of a magnet or a solenoid form a continuous closed loop. Okay, magnetic field lines form the continuous closed loop. This is unlike the electric dipole where the field lines begin from positive charge and end in the negative charge. Okay, here electric dipole field lines from positive charge ends at the negative charge. Okay, or escape to infinity. Electric dipole lines not closed. Okay, magnetic field lines are closed, not electric field lines. So this is the field lines for a bar magnet. This is for this solenoid similar to the bar magnet, but for the electric dipole it is different. So it starts from the positive end and ends at the negative end here. Okay, it is not closed loop. So here closed loop. Unlike electrostatic, the field lines in magnetism do not indicate the direction of the force. Okay, the field lines in magnetic do not indicate the direction of the force. Magnetic field strength. The larger the number of field lines crossing per unit area, stronger the magnitude of the field B. Okay, larger field lines crossing per unit area. 5.3a B around the region, larger around the region 2 than 1. 5.3a. So here it is more than here because this number of field lines crossing this area is more here, but here less. Bar magnet as a solenoid. The magnetic dipole moment of the solenoid is equal to NIA. N is the total number of turns in the loop. I is the current. A is the area. This is a diagram with a small area dx. This point R from the center. This arrangement this arrangement may be used to determine the either magnetic field or the magnetic moment of the needle. Okay, you can determine the magnetic field or the magnetic dipole moment of this needle using this arrangement. The axial field at the distance. Okay, Solenoid. Okay, this is for the axial field because solenoid has axial field only. Thus, the far magnet of the solenoid produce smaller fields. Similar, sorry. Bar magnet and solenoid produce similar bar magnet and similar magnetic field. We at times required to determine the accurately. This is by placing a small campus needle of a now magnetic moment and magnetic moment of inertia. Okay, this is the torque minus mb sin theta, theta angle between the magnetic moment and the magnetic field. Torque is 0 when the needle is in equilibrium. Okay, it is not 0, then it is not in equilibrium. So this is the period of that simple organic motion of that needle. This is moment of inertia, magnetic moment. B is the magnitude of the magnetic field. Okay, this is how we compute the magnetic field from this equation. So the work done in a magnetic field, work done is magnetic potential energy of the final point minus magnetic potential energy of the initial point. Okay, this is final minus initial. Magnetic potential is the final point minus initial point. So when it is in most stable position, work done most stable position means that angle is 0. Okay, that is cos 0, that is 1, and most unstable position is theta is 180 degree. Okay, that is potential energy is minimum at the most stable, that theta equal to 0, most stable, and the maximum at 180 degree, most unstable position. Okay, here they are asking most stable to most unstable position. The moment this is the cost to Tesla conversion. So most stable position theta equal to 0 degree, most unstable 180 degree. Work done, we have to compute from final potential energy to initial magnetic potential energy. Most stable, most unstable. If a bar magnet of intensity of magnetic field is strongest at two ends poles and the weakest at the central region. Okay. So this is the magnetic field at the equatorial line of the magnet. This is at the axial line. So the axial line is 2 times than the equatorial line. So equatorial and axial fields. So axial equal to 2 times the equatorial. This is axial. This is axial. This is equatorial. So axial equal to 2 times the equatorial. Magnetism and Gauss law. It says that the net magnetic flux through any closed surface is 0. Net magnetic flux at any closed surface is 0. These are the various diagrams. You have to find out what is wrong with this, if something wrong. See, the field lines never cross here, so this is wrong. Never cross each other. Earth's magnetism. What is dynamo effect? Okay. The axis of the dipole does not coincide with the axis of the rotation of the but is presently tilted at 11.3 degree with respect to the axis of the geographical axis of the earth. The location of the north magnetic pole is this latitude and longitude placed somewhere in North Canada. The magnetic south pole is in somewhere in Antarctica. Okay, this is the angle of declination, and the angle between magnetic equator and geographic equator is deep. This north magnetic pole behaves like a south pole of the bar magnet inside the earth and vice versa. See, bar magnet and the poles of the earth, they behave opposite. Like, see, north magnetic pole behaves like a south pole of a bar magnet and vice versa. Okay. The radius of the earth is approximately this much. Declination angle. Declination and dip. This is the declination. The angle between two geographic north and the north shown by the campus needle. Campus needle shows a different north direction than the geographical north. The angle between them is the declination. That angle is greater at higher latitude and smaller near the equator. Okay, declination is smaller near the equator and higher at the near the higher latitude, that is near the pole. This is Delhi and this is in Mumbai. Norwegian angle with the angle that needle makes with the horizontal axis is known as angle of dip. Okay, so here this is the magnetic field, this horizontal component. So this angle between these two is the angle of dip or inclination. Angle of dip or inclination. The north pole of the dip likewise. Okay. So this is the relation between this vertical component of the magnetic field, the total magnetic field and the inclination angle. So vertical component equal to B sin I. I is the inclination angle. Horizontal component B cos theta, cos I. Okay. B cos I is horizontal, B sin I is the vertical component. So angle of dip equal to vertical component by horizontal component. At pole, the magnetic field lines are converging and vertically so that the horizontal component is negligible. At poles, the horizontal component is negligible. Magnetism and magnetic intensity. The capital M is the magnetism, that is the magnetic moment per unit volume. Okay, magnetization, capital M equal to magnetic moment small m by V per unit volume. So the total magnetic field is the magnetic field due to the core and the magnetic field due to the wire. These are the relations. Okay, magnetic field intensity, magnetization, magnetic field. Susceptibility is the dimensionless quantity. Okay, magnetic susceptibility. Magnetic susceptibility varies with the temperature. Okay. Mu r is the relative permeability, magnetic permeability. So this is susceptibility for a diamagnetic substance is negative here, and the paramagnetic substance is positive and I. So susceptibility negative for a diamagnetic, susceptibility positive for the paramagnetic. So the H is independent of the Ni or independent of the temperature. Okay. N is the in turns per meter. What is magnetization current? Magnetization current IM is the additional current that needs to be passed through the winding of the solenoid in the absence of the core. Okay, the additional current which needs to be passed through the windings of the solenoid in the absence of the core, which would have a B value C% of the core. Okay, the susceptibility of diamagnetic material is negative, and for para that is positive, and small ferro positive and large. Okay, susceptibility negative for diamagnetic, positive and small for paramagnetic, positive and large for the ferromagnetic. This is the relation. Diamagnetic substance, it will move to a weaker field, so it will repel from the magnetic field. Okay, this is diamagnetic, and this is for the paramagnetic. Okay, that will attract. So completely repelled for diamagnetic, susceptibility negative, and this is 0, relative permeability. Paramagnetic, they have tendency to move to the stronger magnetic field. This paramagnetic, okay, attracted by the magnet. Susceptibility is inversely proportional to the temperature here. Okay, that is Q is constant C. Ferromagnetic substance, they are dealing with the domains. Okay, ferromagnetic substance are which gets strongly magnetized when placed in the external magnetic field. So this is the perfect alignment of the domains. This is the random alignment. Okay, this is randomly aligned domain. This is perfect alignment of the domain. Typical domain size is much. The temperature at which the transition from ferromagnetic to paramagnetic is a Curie temperature, and this temperature is not applicable for the diamagnetic substance, it's only for the magnetic material. Micrometer to meter conversion. Okay, 1 micrometer to 10 power minus 6 meter. Okay, density. This is the Avogadro number. Maximum possible dipole moment is achieved for unrealistic case for which the atomic moments are perfectly aligned. That is the unrealistic case. Hysteresis loop. Substances which have at room temperature retain their ferromagnetic property for a long period of time, permanent magnet. So permanent magnet is a ferromagnet, and at room temperature it retains the ferromagnetic property. Okay.